systems. I know this could go in all sorts of places, and I won't limit you in your questions on that. In fact, I'm going to encourage you, because we've deliberately left as much time as possible for this after 4 brief presentations to have you participate in a conversation around this. So please think about your questions as you're going through, because I'm going to allow plenty of time for that, and I would really like, and so would all the other people on the panel, to hear your thoughts and your questions and have you participate in this very, very important discussion. So our panel today, and I will introduce them in more detail individually, and I'll ask them to come up after all the 4 sessions. We have Mike Davidson, who can put his hand up. Mike is from the Australian Energy Market Operator. We also have Natasha Sadov, who's from Battelle, who's based normally in Columbus, Ohio. We have Professor Thierry Rocha, who's from the École des Mines in Paris, and we also have Simon Troman, a colleague of mine, who heads up our energy sector at the Bureau of Meteorology. So the format today is we'll have each of these speakers speak individually for about 5 minutes. We'll let them all go through their presentations, and then we will convene a panel here, which we're all part of. It's just these people will be facing you and you'll be facing them, and you have to ask them lots of questions. So with no further ado, I'd like to welcome and launch the session. So Mike, over to you.
Just work this out. Whoops. Excellent. Okay, so my name's Mike Davidson. I'm the Manager of Operational Forecasting at the Australian Energy Market Operator, and we basically run the grid in Western Australia and also in the eastern NEM states of Australia. I come from South Australia, so I'm going to be unashamed and talk about South Australia, which is probably, for electricity people, the centre of the universe as far as renewable energy is concerned. You might be surprised to learn. So this is South Australia. It's 3 times the size of Germany, and it's got about 1.8 million people. So it's about the 150th of the population density of Germany, France and the UK. So not many people there. So next slide, please. Okay, so this is the capital, Adelaide. You can see I've been active on Google Maps this week. And Adelaide is where about 1.5 million of the 1.8 million people live. That's our capital city. And not only is it our capital city, but it is a 1,000 megawatt solar generator, from rooftop PV solar generator, which makes an interesting interaction between supply and demand in this area. Next slide, please. Okay, so this is we just picked a day from this month or last month, and you can see here 3 generation fleets working at the same time. So this one here, that's wind, this is solar, and this is all gas. The blue line is the South Australian demand, and the red line is the percentage of renewable energy. So you can see here, overnight, it was very windy, so we had basically the wind fleet providing all the electricity in South Australia. And then as the sun comes up, that wind naturally got displaced, just fortuitously displaced here by a solar fleet. This is the rooftop residential rooftop PV generation, and this is large grid scale solar. And what happened was we had a swap over from a wind fleet, so it was predominantly wind generated, to solar generated, and then as the evening came in, all the renewables dropped off and it was replaced by gas generation. So you can see here, this grey area is gas generation. We maintain that level of gas generation, and the wind generation and solar could have displaced that, but we cap it off. So you can see here, renewable generation dropped from about 100% renewable down to 10% renewable over a 6-hour period. So for from a meteorological perspective, what's important to us is how much energy is it going to produce, each of the weather elements, and what the timing is going to be, and how quickly they swap. So it's really key that we understand and we have measurements in real time or near real time of this fuel. So this is, as Kate said, this is our fuel. Next slide, please. So this is the Adelaide area, and you can see it's basically concreted over, it is a huge heat island, particularly when we get hot weather coming in from the desert behind us, behind the hills. But what you can see here is a parkland that is designed around the original Adelaide city centre. Next slide, please. And you can see here, this is the site of the newest weather observation station that we have in Australia that's operated by the BOM. And you can see it's outside of the densest area of the built-up concreted heat island. Next slide, please. There it is. It's called Nagaida Pira in the native language, and and that means about the sky. Interestingly, we don't have a pyranometer at this observation station, which would be really, really useful for us to verify our satellite imagery from which we try and calculate the output of that 1,000 megawatt solar generator, which is Adelaide. Next slide, please. So this is where the demand is set. So this is the centre of Adelaide, and you can see it's heavily concreted, tall buildings, high density of load, massive air conditioning. So the green parkland outside last year, or this year, got to 45.6 degrees. In here, there would have been areas above 55 degrees C. What we need for the calculation of demand in South Australia is observation, not for climate, but for energy. So we need to know what's going on in that heat island. I can understand, and I really get it, that for climate science, you need to negate that out so you can get some stable long-term measurements. But for energy, we've got to know it. Next slide, please. Okay, and this is the other another interesting point is that we're creating what's called renewable energy zones in Australia. This is southeastern Australia. This is South Australia here. And we're looking at optimal locations for wind generation, solar generation and transmission assets. We create these renewable energy zones. The interesting thing about these renewable energy zones is nobody lives there. So historically we have no weather observations in these areas. Next slide please. So what we're looking to do is work with the BOM, so Bureau of Meteorology, we call them the BOM, and we're looking to collaborate around getting more accurate measurements of demand. So that's including heat islands, including cool changes from the sea, and also the progression of troughs and fronts, so that we can predict and get situational awareness on weather in real time. And we're looking for real-time and observations and also forecasts for wind and solar in those renewable energy zones. So that means more observational infrastructure. And what we want, because I've created a data science within our forecasting team, data scientists just want more data more often. And we want to put that out to the meteorological industry right across Australia, so that they can put their innovation and science on it and give us the very best forecast back. And that concludes my very brief presentation. Thank you.
Thank you, Mike. I actually neglected to introduce you properly because I'd introduced you more generally. Now, Mike's about 25, but because of that supply and demand graph that you saw up there, he and his team of 14 people try and balance supply and demand on a minute-by-minute basis across 4 states. 4 seconds, sorry, 4-second basis, across 5 states, 1 territory, 45,000 kilometres of transmission line. How many thousand kilometres distribution line? 800 and something. It's a very big piece of infrastructure, and its ability to supply the various Australian cities and communities is very much dependent on our ability and their ability to be able to get that real-time Earth observations data into their decision-making. So there's a good one to kick it off with. Now I'll turn to Natasha Sadov. Natasha's a principal research scientist at Battelle Memorial Institute, as I said before, in Columbus, Ohio. She's been there for 11 years, contributing to environmental governance projects in areas like energy management, air quality, climate change, and she's particularly been looking at the translating science into environmental indicators, training materials, and so forth. So she's really in the how do we convert the science into usable information. She's been engaged with GEO in various roles over the past 5 years, most recently as the principal investigator of a NASA grant under the auspices of the GEO Vision for Energy, GeoVeil. She's been working with electricity utilities, end users, the sorts of people that Mike deals with on a day-to-day basis, as well as the operator of the grid. And she's been looking at how you can better access and supply NASA data for energy management and resilience planning. So I'd like to welcome you, Natasha.
Thank you, Kate. Good afternoon. Very nice to be here. Thank you very much, Kate, and all the organizers for getting us here. So I'm going to bring this all into the context of GEO, since this is GEO Week. So I'll talk a little bit about GeoVeil and the contributions that NASA and the European Commission are making toward this initiative. Next slide, please. So, and you can click twice. Oh, I have it. Now, this is the moment of truth. Can I figure it out? Okay. Yes. So GeoVeil was established in 2016 to ensure that there was a link between the renewable energy community and GEO, and also to make sure that Earth observations were being appropriately used and applied for energy decision making. So as Kate mentioned before, this is particularly relevant today given the Sustainable Development Goals. Sustainable Development Goal 7 is energy access for all. Energy touches on all of the Sustainable Development Goals, particularly related to poverty, related to development. So it's a very important context that we understand renewable energy and kind of understanding not only the relations to development, but also with regard to the Sendai framework, the Paris Accord. There's lots of important relationships that I want to highlight. That we start with renewable energy and we think about the ways in which we're using Earth observations, but extending that to disaster risk reduction, to resilience, and to climate are important connections to make. Next slide, please. Or do I do it? Okay, fine. I'll do it. So I won't read these. I just want to highlight a couple important elements from our GeoVeil goals for 2019 through 2020. We just submitted our implementation plan for these coming years. So I think the most important things that you can see here are the end-to-end energy systems and energy management networks, promoting collaboration. Part of what I'll touch on and what I hope that maybe we can even have a question about is how do we ensure that we're all talking and that we have the right people in the room, that we have the right voices in the conversation to ensure that this data is being accessed by those who need it in a way that they can actually use it, which is a lot of what I try to focus on in my work. But also the policy relevance of Earth observations that are available. And like I said, encouraging the use of that information by various audiences. So these relate to the planned activities that we have for the coming years. We most important, want to note that we're doing our best to connect to additional and new geo regions, geo work initiatives, work plans. We're here, excited to be here in Australia, so the connection to the to AOGeo is particularly exciting. We have a lot of strong connections to EuroGeo. We want to continue to strengthen new collaborations and new relationships across additional regions, AmeriGeo, and others. So we're excited. I think if there are ideas, that's something else I'd love to hear from, maybe during the questions. If you have other, I won't get into any of these for time's sake, but if there are other questions about some of these specifics, we can definitely talk about them. So to get into just a couple minutes on some of the commitments around the world toward GeoVeneer, NASA has funded two grants under Geo. This is the one that I'm working on. So it's a capacity building grant. I am a social scientist. I'm actually a human geographer, so this is a little bit different of an activity because I'm not actually producing a data set. So what I'm looking to do, we're about halfway through, or so I guess what I am doing is we've identified a specific set of possible data end users in electric utilities. There's a lot of NASA data sets that are relevant to energy, but there's not one specific resource that is just, off the shelf useful for this end user group. So a lot of what I'm doing is looking alongside stakeholders and end users out of what's available. Is this the right decision-making scale? Is it meeting the needs of this end user group? So that obviously has to start with what exactly do they need? What are their main issues? That could be with regard to renewable energy and how they can incorporate that into their management portfolio, incorporating that into the grid, or it could be looking at resilience questions related to extreme weather, fire risk, drought, depending on the region in the United States, that varies. If you have any questions about this project, obviously I'd love to talk about that more, but this is one of the grants that NASA is supporting. The other grant is more of a traditional NASA research project. So this one is a colleague out of the western US at UCAR. He's looking at nowcasting, combining satellite data with models, and getting a irradiance product. So if you have questions about that, can get into that. So two very different projects that NASA is supporting in this within GeoVeneer. But then also Horizon 2020 from the European Commission. I wrote it down so that I could do justice. It's a part of a framework program. So even though there are several projects that are related to Geo, two of them specifically pilots on solar energy, and there's an additional three that are two on solar and one on offshore wind. So there are resources that are being put into GeoVeneer from NASA and from the European Commission. I think we're all trying to get a little bit more engagement across, like I mentioned before, across the entire Geo network. So we think there are other projects that are relevant to the goals and to the scope of GeoVeneer, so we're excited to kind of learn about those and see how we can coalesce a more prominent community around energy management, renewable energy. So I think with that, I'll stop within my 5 minutes. So thank you.
Thank you very much, Natasha. There's plenty of seats in here, so come on in. Don't wait up the back. We've got lots more exciting stuff to come. Our third speaker today is Professor Thierry Rocha. He's currently the director of the Centre Observation Impacts Energy at Mines Paris Tech, which is at the PSL University. His research centres looking at how you use Earth observations around renewable energy resources and assessment of environmental impacts of energy uses, both in the past, today, and into the future. His research interests are mapping geophysical parameters for renewable energy studies, and climate and renewable energies. He's been involved in GEOS since 2005. He actually created the Geo Vision for Energy, the VENER initiative that Natasha was just talking about, and is currently co-leading it. He's been appointed in 2015 to the Geo Program Board as France's representative to that, and he's coordinating the newly awarded H2020 E-Shape project. So I'd like to welcome Thierry to the stage, please.
Thanks a lot, Kate. So I'd like to make a short presentation, not talking about project, but trying to see what Earth observation can do for supporting renewable energy-powered electricity grids, or at least the inclusion of this on the grid. So first we have a small presentation about what we have.
The sun is the primary natural source of energy. 1 hour of solar radiation at the top of the atmosphere is greater than our annual global energy consumption. Our photon is now at the top of the atmosphere. It will interact with the atmosphere that may absorb or scatter it, potentially preventing it from reaching the ground. UV high-energy photons are partly absorbed by the ozone and impact human and animal health.
It's not the good one, sorry. That's okay.
Australia's proximity to the equator, combined with fair-skinned population, means a danger of skin diseases. Australian government agencies, the Bureau of Meteorology and ARPANSA use CAMS UV service. They've developed a smartphone application called SunSmart, reaching nearly 500,000 downloads. If not absorbed or deviated by scattering, our photon may contribute to solar energy. Even with a clear atmosphere, gases, water vapor, and aerosols can absorb and scatter our photon. The CAMS Clear service predicts clear sky surface solar irradiance worldwide. It accounts for over 200 registered users for more than 3 million automatic requests in 2018. Clouds are also obstacles for our photon to reach the surface. The European-funded project GeoCradle has developed a solar radiation nowcasting system. It has been demonstrated in the Egypt region with the Ministry of Electricity and Renewable Energy by the provision of the Solar Atlas of Egypt. SENS provides information for existing and future solar power plants. Based on SENS and CAMS data, 20 government areas are targeted for the construction of photovoltaic farms. Our photon can travel everywhere, including cities, where more than half of the Earth's population is living. Shadows from buildings and orography are affecting solar PV or thermal rooftop installations. The European-funded project NextGeos allows computation of rooftop solar energy potential in complex environments. The French SME, In Sun We Trust, has endorsed this initiative of high-resolution solar cadastre for urban agglomerations in France. The EuroGeo and GeoVision for Energy Geo initiatives address the Sustainable Development Goals and exploit European infrastructures including CAMS, C3S, EASE emissions, and DIAS. The European-funded project eShape gathers 54 institutes and companies to develop 27 pilots organized in 7 showcases addressing numerous SDGs. 2 energy pilots on solar energy will be developed, 1 extending the SENS application, and 1 addressing the photovoltaic high penetration in urban areas.
So when that was a general context on where we are working, now let's focus on what we are doing to solve this challenge in terms of penetration of solar energy in the urban area. It's a bit different in maybe that what was presented by Mike before, but we have not such development of renewable energy with solar panel on roof in France. And so the idea is first to create what is needed to have more and more PV system on urban area. So that was work that was presented in the video, and you have a nice website that allow you to have a good demonstration of this. And nowadays, I think more than 60% of France was covered with all this cadastre in order to allow the people to contact the good person that can put a PV system on their house and having a production that can be a self-consumption or a production for the grid. Looking to this challenge of variability, which is key in including all the renewable energy on the grid, as shown by Mike. You see this idea of the variability of the production during the time. One of the challenges is first to understand this variability and to be able to represent it. So we talk about the spatial one and also about the temporal one now. This is what is shown on this scheme with the variation on the day. It's an accumulation for all the panels that are in this area, showing the difference of production on each of them. So really the challenge is to take into account the structure of the city in order to have all the shadow, the clouds moving and so on and so forth. Now, sorry. Also, when we are looking to a urban area, at least in Europe, what is also of interest is this forecasting of solar energy in the area. So there is a need to have this high quality of local and spatial aggregated solar forecasting in order to process that as a kind of aggregated farm, given some input in terms of time horizon and resolution for different usage. We try to have a set of this usage there for the instantaneous consumption, but also for the balance, and also for the dispatching. And also behind that was not shown by Mike, but I think there is also the solution of the storage, which is here, and should be also evaluated. And also because of the market in Europe, which is open to trading, there is this question about trading the energy on the market. So the idea is really on the optimization of the solar energy production for all this usage and for sun tracking and have also this adaptation for big farms. So that's a big challenge to coupling all the different EO sources, so the in-situ pyranometers, the solar camera, which are very expensive. So we are trying to develop a new system based on fisheye camera, for the one that are used for surveillance, in order to look on the sky and to include the information that can be extracted from that, and to provide them with satellite and NWP on different forecasting techniques, and given the best of this, to offer the seamless of solar forecasting a long time with different areas. And just to, when we are talking about all this type of information, in situ, models, satellite, we try to show, and we have done a work that has been achieved last year with the electricity operator in France, EDF, integrating satellite, the models, also the information about the clouds and the top of the clouds, and a fisheye camera. Here you have only what is seen by this fisheye camera looking to the sky. And to model this in order to have also the possibility of model the shadow that is brought by all the clouds on the land that will impact really this. And so we are really trying to include all the available information from the in-situ, from the camera, from all Earth observation which is available in GEO and also in all European assets, in order to really give some tools to the operator to go further and to improve the penetration of renewable energy on the system. Here are the contact of the people that are operating this. I acknowledge their work. It's really an amazing work which is done there, and really I hope it will open some elements for the discussion. Thank you.
Excellent. Thank you, Thierry. Our last speaker before we move to the panel session is Simon Troman, who's the energy lead within the Energy and Resources program that I lead at the Bureau of Meteorology. He's got over 30 years' experience throughout the renewable energy sector, covering aid development, government, commercial, project management and research roles. He's the former CEO of ITP Power. He's been on the advisory panel for ARENA, which is our renewable energy agency, and he's worked extensively not only across Australia but also in Africa and the Pacific. So we're very lucky to have him and to listen to his perspective today on some of these challenges that we're all tackling. Thank you.
So I figure I've spent years building the equipment and the systems that are causing Mike to have sleepless nights, so now I probably should work on the solution to the problems we've created. Can you imagine going to an oil and coal conference and not having a whole stream dedicated to the fuel source, to understanding your supply chain, understanding the efficiencies of burning it better? Every large oil and coal conference you go to would have multiple streams covering the fuel source. I've been to more renewable energy conferences than I can remember, and they don't have whole streams covering the fuel source, the weather. The technology's covered, the technological answers of how can we make better systems, how can we bring battery systems in, how can we better control the generation source or the transmission source. But now the other part of the puzzle needs to be answered, which is understanding our fuel source. And we've seen Mike, Natasha and Thierry cover some different versions of doing this. The Bureau is working with AEMO on that very solution, that very problem of how do we better understand our fuel sources with an aim of taking the idea that renewable energy generation is non-dispatchable, intermittent, all those words, and turning into some sort of semi-dispatchable. Can you predict to a reasonable level of accuracy how much you're going to generate and when, and what timeframes you might be doing that in? This is one of the next major pieces of the puzzle to end up with a secure, stable and clean energy network. A few times in the presentation here, and also it's just a general thing you see talked about all the time with renewable energy, is the word penetration. And it's an odd word because depending who you ask, you'll get a totally different definition of what it means. Some people refer to definition as the amount of available roof space. 40% penetration, it means 40% of the available roof space has got PV on it. That's not particularly useful to AEMO and the market operators. They need to understand their problem with penetration is what is the amount of unpredictable or undispatchable energy meeting the demand at that moment in time. Because penetration doesn't really matter for the rest of us. What we care about is contribution. How much of our energy supply is coming from renewable energy or clean energy over a course of a period of time is what we care about. But for the market operator, it's all about the penetration at that moment in time, or what's going to happen in the next 5 minutes or half an hour. How much is going to come from energy and how reliable is that estimation? I'm going to just dwell on it a little bit. Kate mentioned my background has a lot to do with the early days of renewable energy, which of course all took place off-grid. We didn't work on the grid in those days. All the early innovation took place off-grid. When I first started in the industry, 30% was considered a limit. You could not put more than 30% wind or solar on. There's no point talking about other renewable energy generation because it didn't exist back then. Wind and solar, you cannot put more than 30% into a given contained system. We pretty quickly passed that just by thinking in different ways. People like SMA developed fuel saver technology, which pushed it to the general accepted term was 50%, about 50% before you need to put lots of storage in. Better battery management and falling storage costs soon saw us go past 80%. And then when we started to realise that the world didn't break and the light stayed on, we started pushing it higher. The Tokelau Renewable Energy Project was the first in complete nation to go 100% solar. We didn't turn the diesels off, we decommissioned them and took them away. The entire nation runs on solar, with batteries. Pretty expensive solution, but battery technology is coming down in price all the time. Coral Bay here in Australia has no batteries. It has wind turbines, 2-speed wind turbines that change their output as the speed velocity goes up. So we have wind turbines and diesel generators combined with a flywheel, and Coral Bay has run for up to 3 days with the diesels turned off and runs most of the time with no diesel contribution. So what was the point of all of that? The next problem is with our grid. Where do we take our grid? I'm not trying to say that grid solutions are as easy as, say, a small off-grid system, but given that it wasn't that many years ago that we said 30% was the limit for penetration on a contained system, and then we pushed through that in no time at all to the point now we're running with our diesels turned off or decommissioning them, the big grid, the NEM that Mike controls, is going to go through the same pattern. It's going to go more and more higher penetration, and it's going to constantly challenge our understanding of what a stable grid is with renewable energy in it. Part of the puzzle, something that Mike touched on a moment ago, and both Natasha and Thierry also brought out, which is the demand side of it is becoming a problem. There's not just the demand side that was talked about, which is What's the temperature going to be in downtown Adelaide? Is it going to be 50 degrees? Is that going to cause all the air cons to run really efficiently and flat out and have high demand? We're also seeing a massive boom in rooftop solar around the world. Mike mentioned Adelaide's now a 1 megawatt power station. About 1 megawatt rooftop solar in Adelaide? 1,000 megawatts of rooftop solar in Adelaide. Do you sleep at all? So you've got this rooftop solar. Problem is, the bulk of the rooftop solar is behind the meter. The bulk of the rooftop solar is not seen by the market operator. When that was a scattering of 1 kilowatt PV systems on a few houses in the suburb, nobody cared. But now you've essentially just built a large power station in your city that the market operator has no oversight of. What do they actually see it as? They see it as a drop in demand, not a generator coming online or going offline. So now you've got a situation where, look at an individual house. Is that house on a sunny day, is it drawing 4 kilowatts or 14 kilowatts? And is it drawing 4 kilowatts and another 15's coming from the rooftop system? These predictions now are becoming critical for the market operator to embed sensors and things throughout the, or find a way, whatever the technology is, throughout the high demand centres to understand not only what is the likely demand going to be, but also how much that's going to be contributed by the behind-the-meter solar. This is about to become critical because you've now got 1 megawatt behind-the-meter systems coming online in Australia and other parts of the world. Mike touched on one of the key issues is that the siting of our weather stations over the last however many decades has been more about getting the right scientific answer for weather forecasting and understanding weather and climate, not for an end user like the energy market. So we need to develop a new way of thinking of how do we now site our weather stations and how do we now model our weather for an end user such as the energy sector. And that'll be quite different to what it might be for a pure science approach. For example, Mike touched on the fact that the weather station in Adelaide is sited in the place that's going to give it the cleanest air, if you like, the best conditions without interference. We might want to put another sensor right smack in the middle of Rundle Street Mall so we can see what the temperature difference is, what the humidity difference is. The bigger one that I think is going to be a worry is the nice clean air site one is going to drop in temperature much quicker. The ones in the city with all the concrete around them are going to hold the heat a lot longer. We need to understand down to that sort of level. Natasha touched on that link between the RE industry and the geo, and I think that is becoming another critical part. I was very interested, Natasha, that your background of human geographer rather than engineer, because I think the engineers are happily getting on with the technological answers and forgetting that we actually need to work with what are the people doing, what's the human impact, when are we turning our air conditioners on, all those understandings. The best thing I learnt from Thierry's presentation was that we should be putting our solar panels at the top of the atmosphere because apparently we can sort all the problems out with 1 square metre's worth of solar panels. I think that pretty much concludes where I was going to go. Yes, that does conclude where I was going to go. There you go. Thank you.
This is on. Okay. More on. There you go. You figure that one out. Okay, thanks. We've probably only got about 15 minutes, so I'm hoping that a few of you have got your questions, but I'm going to kick it off with the one that Natasha actually said she wanted me to ask in the middle of her presentation, which I'm not going to phrase it quite the way you asked it, but I'm interested, maybe starting with Natasha, is what do you think is going to make the biggest difference in the transition to getting an appropriate level of Earth observations that can allow us to manage the transition to renewable energy? You said, how do we make sure we're all talking? I'm interested in everybody's thoughts about whether it's about awareness, which is a lot of the work that you've been doing, awareness in education. Is it about the technology that we need in order to manage it? Or is it about the financing? So what are sort of the things that will help us get faster towards the sorts of energy observation system that Mike's called for, Simon has described, Thierry has given us some solutions that are being experimented with. So first of all, how are we sure we're all talking? And if it's not just about talking, how do we move through the other technology and through the financing?
Well, I guess just real quick, I would just add, thank you for starting with that excellent question. I I think it's not just are we all talking, I think that's really the start, because not to say that the technology and the science is or is not out there, but if it is out there, is it meeting the needs of those who need it? And so that's why I think sometimes it's not a question of science. The science is out there, but do people know about it? Is it meeting their decision-making needs? Are the units appropriate for the private sector, for the utility sector? So that's why I say I think the communication is really critical, so that the science and the models and the data that's out there is able to be translated for decision-making specifically.
Okay, I might ask Thierry then, because you say the science is out there, but we've heard that NASA's doing some solar nowcasting. We've heard that the EU's doing solar nowcasting. The Bureau has a solar irradiance product, which doesn't quite get to nowcasting yet, but we're getting there. What is happening in the science that's filling a gap? Because Natasha says that it's about awareness.
Yeah, thanks for the question, and thank you for giving me the opportunity of presenting. I think in the question we have when we are talking about Earth observation and the use of the Earth observation, it's really what is the quality of this data, what is the strengths, and can we believe on that? Are they reliable? Are there something that anybody can trust in order to be able to do what they want after that? And that's the question we have most often when we start on our project, and even on CAMS radiation. That was a production of a daily solar energy production, or at least information. And nowadays the question is out. So the people are ready to use it. They are trusting the data. It's reliable. We know the precision. We know the accuracy. We know what we can do with that. And so the next step is really including all these data sets in the daily work or the daily usage of the different people. And that's the point we are working on. And now we go to the question about the evolution of the power, or the quality of the solar energy or the wind during time, and with which precision, and is it reliable, looking to in situ measurements, and how can we manage all these topics. And mostly all the people are okay now to use it without questioning the quality of this. And that's a key step that was reached, and that's a good point in my view.
Do we have a question from the audience? Come on, I've given you heaps of notice. Yes, we have one. Could you introduce who you are? And I'll take the other speaker back. Thank you. Introduce yourself and your organisation and ask your question. Thank you.
Hello, I'm Haris Kodoes. I'm from the National Observatory of Athens. I would like to ask all the presenters about the Earth observation and the value of the Earth observation in the development of the relevant services in the renewable energy domain. Actually, do you have any assessment, any measure of what has been the market, how it has been developed in terms of prices, and what has been the main change, let's say, in the industry using the Earth observation? Thank you.
Looking, a bit of extra clarification required on the question? No, Mike will have the mic.
If I think I understood the question correctly, you were asking about the value and number of participants in the meteorological market supplying the energy industry, is that correct? So this is a really important question for AEMO. Up to now, we've relied on a single wind and solar forecasting model that Thierry was active in at the beginning. We do have 2 or 2.5 weather vendors providing us forecasts. What we're looking to do is to really upscale the capacity and capability of weather vendors providing services into the Australian market. We're also trying to get those vendors to cross over into the energy industry itself by not only providing weather characteristic forecasts, but also converting those into megawatts of demand and solar, so linking up with energy businesses. So that's one of the strategic objectives that I have as a forecasting manager, is to really build that capability. What we're trying to do in AEMO is replicate what's happened in the weather industry by moving more towards consensus and ensemble forecasts, so that we can create truly reliable probabilistic forecasts. Because it's clear, particularly in wind forecasting, you'll never ever get the right answer. So the best thing you can do is work out what your variation is going to be, your uncertainty, and make or take that information and give it to the people who are actually running the grid, so that they can put the right assets in place to manage that variability. I hope that answers your question.
Do we have a second question that someone would like to ask? Well, we have one here in the front.
My name is Pedro Zwalen. I'm the ambassador of Switzerland. The example of Adelaide showed very impressively, actually, that between wind and sun, you need a certain redundancy and complementarity over a longer time. Now, when both fall down, then you got a problem. Does that mean that on the long term, we just need to search for more diversity in sources? Say you include wave energy production in close to the sea, and then you might end up with more complementarity. This is the first question. And secondly, do we need just to invest into redundancy and say, okay, instead of having a gas energy production, we just invest into a wave energy production, despite knowing that we might not use it actually all the time?
Okay, that's what in South Australia we would call a gnarly question. Look, as far as running an electricity network, first of all, what you want is certainty. So you want the very best forecast you can get. Once you've got as certain as you can get, then what you need to do is understand the uncertainty. And you need to understand the uncertainty around the amount of energy that you can get from each of your renewable energy sources. You need to know what their peak is going to be, and you need to know what their variation is going to be. And that's either going to be variation that Thierry showed during the day, or when they ramp out, because management of variation and ramping is absolutely critical. Then what you need to do is work out how much energy storage you're going to require to manage all those factors, because you can do that, and what type of energy storage you require over different timescales. So you might have some down below sub-second that provides you with fast responses, and that might be a battery. During the day, you may have pumped storage that enables you to cover dips in your energy, your intermittent renewable provision. And then you need alternative fleets of generation that can say, for example, take care of a wind drought that might last for a month. So what you need to do is have a variety of resources. Diversity really helps. But what the most important thing is to have sufficient understanding of the amount of energy each of your resources is going to provide, how it interacts with other sources, and the uncertainty and the speed of variation. I hope that helps.
Yeah, Mike, just to add to that, I think one of the things that might be quite different here, not with everywhere, but is the sheer scale of the grid. So when there's a bad weather event in one, a non-producing weather situation in one area, from wind or solar, say, because of the interconnectivity over 4,000 kilometres, there are other places that will be producing as well. And as Mike said, pumped hydro is a phrase that we use quite a lot. I'm not sure if everybody's familiar with it, but that's about pumping the water back up at a time when there's excess availability of renewable energy in the grid, you pump the water back up again and then let it run down at a time when you do need it. So it forms a form of battery. And in fact, Tasmania in Australia is looking to be the battery of the nation because of its access to hydro. One last comment, and then I know we have speakers who are starting at 3:30.
I was actually going to say much the same thing. It's not just technological generation diversity, but also geographical diversity. And there's been a lot of modelling done into that. And some of the modelling suggests that there's never a time in Australia that it's not windy somewhere to enough to generate quite a lot. And the grid is fairly interconnected and becoming more interconnected. So as more interconnection goes in, geographic diversity will play a major part as well.
Obviously, there are some hazards associated with the interconnectivity, as there are good aspects. I would like to thank very much all of our 4 speakers today. I see people are piling in for the next one. You missed a really good session here, guys. You should have been here earlier. But I'm really glad that we heard from all 4 of you. I think you've shared some wonderful insights. It's a complex problem. It's an important problem. It does promote the Paris Agreement. It promotes the Sustainable Development Goals, not just 7, but quite a few of the other ones are dependent on the answers that we're seeking for quite a few of the questions posed today. And of course, disaster resilience is not the least of those as well. So thank you very much for all of you coming and joining us. Thank you to everybody here. And look forward to the next session.